So a bunch of problems on the sheet. 1a, we need to sum up 1 plus 2/3 into half plus 2/3 into 5/6 half squared plus so on and so forth up to infinity. Right? Now this could be written as, just rewritten as 1 plus minus 2/3 into minus half, right? Plus minus 2/3 into minus 2/3 minus 1 into minus half whole square and so on and so forth, right? So which is like 1 plus nx plus n into n minus 1 by, there must be a 5/6, so 2 to bring it, to make this 5/6, a 2 factorial x squared plus n into n minus 1 into n minus 2 by 3 factorial x cubed, etc. up to infinity. That's going to be 1 plus x to the power n. 1 plus nx plus n into n minus 1 by 2 factorial x squared and so on and so forth up to infinity is going to be 1 plus x to the power n. So this is 1 plus x to the power n, which is minus 2/3. That's going to be the sum of the series, right? Got me right on this? Let's look at the next problem. We want to be able to find the number of distinct terms in the expansion of this multinomial, if you remember. Now, any term, when you expand this, would be of the form x1 to power alpha 1 into x2 to power alpha 2 into xn to power alpha n into a constant. Any term would be of this form, where the alpha i's will assume values from 0 to 3, isn't it? The alpha i's will assume values from 0 to 3, yes or no, right? The important thing is that the sum of these alpha i's must always be 3. Sum of these alpha i's must always be 3. So the number of ways in which these alpha i's could add up to 3. The number of ways in which these alpha i's, of course these alpha i's are whole numbers, right? These alpha i's are whole numbers, 0, 1, 2, 3. These are the permissible values of these alpha i's, right? So sum of these alpha i's for any term must be equal to 3. And the number of such alpha i's that we can have that add up to 3, number of whole numbers that we can have that add up to 3 will give me the number of distinct terms, number of dissimilar terms, right? Now, again, go back to partition days. What we do is, we convert these alpha i's that are whole numbers into natural numbers by adding 1 to each one of them. So if I add 1 to this will become 1 plus alpha 1, 1 plus alpha 2, 1 plus alpha n equal to n plus 3, where the 1 plus alpha i's will be natural numbers. 1 plus alpha i's would be natural numbers. So 1 plus alpha i's are beta i's that are natural numbers. So then what we are seeking is the number of natural number solutions to this equation. What we are seeking is number of natural number solutions to this equation. Now, the number of natural number solutions to this equation, if you remember, yes, by constructing towers, it's like 1 plus 1 plus 1 plus 1 plus 1. How many times? N plus 3 times is going to be N plus 3, right? So now in these N plus 1 ones, how many pluses are there? N plus 2 pluses are there. Out of these N plus 2 pluses, how many do we need to select? N minus 1. See, these are N minus 1 variables. So these are N variables. So we need how many of these partitions do we need? N minus 1 partitions we need. So that N variables can be created. One would be beta 1, one would be beta 2, one would be beta 3, etc. How many partitions? N minus 1 partitions from N plus 2 available, from N plus 2 available. And that could be done in N plus 2 C N minus 1 ways, which is the same as N plus 2 C 3, which is the same as N plus 2 C 3. NCR is NC N minus R, etc. Right? So the number of dissimilar terms in the expansion of this is going to be N plus 2 C 3, N plus 2 C 3.
Conditions when all the three terms are at the same time means all the S's x1 cube like all these, so that would be N, and when all the three terms in the same term, that x1 x2 of different kind, that would be N into N minus 1 into N minus 2 plus like 2 are of the same kind, N into
I got you, but again, realize that if I had increased this, then it would add to your tragedy, right? That would have been a problem. Therefore, the reason I taught multinomial and a formal multinomial approach was this. The reason was simply this, right? So, must remember this. The number of solutions then is going to be N plus, number of dissimilar terms in the expansion of this is going to be N plus 2C 3. Okay. I do want you to go back and read the partition stuff one more time, the one that I taught way back in class 11. Make sure you read that, make sure you understand that. We next want to find the coefficient of x power 49. We want to, in problem C, 1C, we want to find the coefficient of x power 49 in x minus C1 by C0 into x minus 2 squared C2 by C1 into x minus 3 squared C3 by C2 into x minus 50 squared C50 by C49. We want to find the coefficient of x power 49 when I multiply this out. These are 50 factors, as you can see. These are 50 factors, and I want to find the coefficient of x power 49. Very clearly, the coefficient of x power 49, as you can see, is going to be minus C1 by C0 plus 2 squared C2 by C1 plus 3 squared C3 by C2 plus 50 squared C50 by C49. That's going to be the coefficient of x power 50, x power 49, beg your pardon, right? That's going to be the coefficient of x power 49, right? Now, which means what we are trying to do is the summation minus the summation of r squared CR by CR minus 1. Yes or no? R squared CR by R minus 1, where R runs from 1 to 50. And if you remember, again, NCR by NC R minus 1 is N minus R plus 1 divided by R, right? N minus R plus 1 divided by R, which then leads to minus summation R squared N minus R plus 1 divided by R. R runs from 1 to 50. Yes or no? This, of course, this is 50 minus R. 50 minus R. So this is like summation minus summation R into 51 minus R. R runs from 1 to 50. You can find the summation. right? Because 51 summation r minus summation r square, right? So I'll leave it at this point. Okay, let's look into the next problem. S equal to NC0 x to power 3n plus NC1 by 2 x to power 3n minus 1 into 3 minus x cube plus NC2 by 3 x to power 3 into n minus 2 into 3 minus x cubed whole squared plus NCn divided by n plus 1, 3 minus x cubed whole to power n. We want to be able to deal with this. Essentially, what's the formation here? This is summation NCR by r plus 1 x cube whole to power n minus r 3 minus x cube whole to power r, where r runs from 0 to n. R runs from 0 to n. Yes or no? That's the way it is. This is the summation that we are seeking. Now, this r plus 1 is really the stumbling block. We need to deal with this. So let's simplify matters here and see what we could do with this. NCR by r plus 1 is actually n factorial n minus r factorial by r factorial into r plus 1, right? We have a r plus 1 factorial here, and this is n plus 1 minus r plus 1 factorial. So it would have been nice if this was n plus 1 factorial. So now to make it a n plus 1 factorial, we multiply and divide by n plus 1. Yes or no? So this becomes like a n plus 1 factorial by, this is r plus 1 factorial, and this is n plus 1 minus r plus 1 factorial. So this is 1 by n plus 1, n plus 1, c r plus 1, how about it? 1 by n plus 1, c r plus 1, that's what this reduces to, right? Now this n plus 1 is independent of the running variable r, so it can wriggle out of the summation, make life a little simpler, isn't it? The r plus 1, the running variable sitting in the denominator, was a bigger impediment, but now n plus 1 can come out of the summation, right? Can come out of the summation here, will make life simpler for us, right? So what we do here is, we write this as summation n plus 1 cr plus 1, the 1 plus 1 by n plus 1 conveniently pushed out, x cube whole to power. This n minus r I can write as n plus 1 minus r plus 1, right? And this 3 minus x cube, see, NCR a to power n minus r, I would have liked this to be to the power r plus 1, right? So what? Let me force it that way. 3 minus x cube whole to power r plus 1. Now, essentially I multiplied by 3 minus x cube numerator, so I can divide by 3 minus x cube, and 3 minus x cubed is also independent of the running variable r, so that can also walk out of the summation sign. So along with n plus 1, we have 3 minus x cubed coming out of the summation sign, right? Where r runs from 0 to n. Now, See, when R runs from 0 to n, things are perfectly alright in terms of a full binomial sequence, except that, the term, it starts with n plus 1, C1. It should have started, if it started with n plus 1, C0, then life would have been so much better. It would have been a complete binomial rhythm. Yes or no? If it would have started with R equal to minus 1, then this would be NCR a to power n minus R x to power R. A complete set of binomial terms would appear. Yes or no? So, which means the only problem is No. Why? Start from R equal to minus 1 and subtract the term corresponding to R equal to minus 1 here. Yeah. Right. Oh, okay. You did that mentally and said, okay, R equal to minus 1 and subtract the term corresponding to R equal to minus 1. The term that corresponds to R equal to minus 1 is, outside this summation, of course, outside this summation is n plus 1 C0 R equal to minus 1 means this will become n plus 1. This will become n plus 1. N plus 1 and this will become to power 0. Yes or no? This is the term to be adjusted. This is the term to be adjusted. Does it make sense? The term corresponding to R equal to minus 1, which was the only term missing in a complete binomial expansion, that I added in the summation and manipulated outside the summation. That's what we did. Tell me. This then is what? Yes. A to power n minus R, B to power R is A plus B whole to power n plus 1. A plus B whole to power n plus 1. So x cube plus 3 minus x cube whole to power n plus 1 is what transpires there, right? So then this is as simple as 1 by 3 minus x cubed n plus 1. This would be 3 to power n plus 1 full binomial sequence minus x to power 3 n plus 1. That's the required summation. Make sense to all of you? I hope all of you realize how this is like NCT, A to power n minus t, B to power t kind of a term, right? Where t runs from 0 to n plus 1. T runs from 0 to n plus 1. Isn't it? Confusion? No? Let's look at problem E. How many of you have school exams going on right now? You have school exams going on, Haryana? School exams? Okay. E. Now, how do we deal with this? How do we deal with this? We have this and we want to be able to establish this. You need to look at one thing. Take clue from some of the things that are spread out in this expression. An, for example, is the coefficient of x power n in this. Now, where on earth then did these 2ncn, 2n minus 1cn, 2n minus 2cn, ncn emerge out of? We need to know how they came into being in the equation or the expression, right? That has to be understood. Now, what is 2ncn really? Coefficient of x power n in 1 plus x power 2n. What is 2n minus 1cn? 1 plus x power 2n minus 1. What? With a minus sign now. X power n in 1 plus x power 2n minus 2. X power n in 1 plus x power n. This is alright, but the minus signs now. This minus 1 to power n must have been, this minus 1 to power n ncn must have been the coefficient of x power n in minus of 1 plus x whole to power n. Yes or no? Minus of 1 plus x whole to power n. Minus 1 to power n ncn must have been coefficient of x power n in minus of 1 plus x power n. Because see, this minus 1 to power n comes out and coefficient of x power n is ncn, right? This 2ncn must have been the coefficient of minus of 1 plus x power coefficient of x power n in minus of 1 plus x power 2n. Since minus squared, it will become plus. Then 2n minus 1cn must have been, this minus of 2n minus 1cn must have been the coefficient of minus of 1 plus x to power 2n minus 1 must have been the coefficient of x power n in this, because then minus 1 to power 2n minus 1 must have been minus 1. Do you all realize that? Which means if, see, this 2ncn comes married to a2n, 2ncn comes married with a2n. So now, if instead of x, I had a minus of 1 plus x here, instead of x, if I had a minus of 1 plus x, then this would become minus of 1 plus x to power 2n, and the coefficient of x power n here would have become minus 1 to power 2n, a2n into 2ncn, yes or no? And same with other terms. Instead of x in this identity, if we had a minus of, I'll repeat. See, for example, 2ncn. How did we arrive at 2ncn? 2ncn coefficient of x power n in minus of 1 plus x power 2n. 2n minus 1cn, minus of 2n minus 1cn would have been the coefficient of x power n in minus of 1 plus x power 2n minus 1. Because minus 1 to power 2n minus 1 would have given me a minus sign and x power n from 2n minus 1cn, yes or no? Right? So now a2n into 2ncn, where would that have come from? If instead of this x, we had a minus of 1 plus x, then the coefficient of x power n in this would have been a2n minus 1 to power 2n, which is plus 1, into 2ncn. And same with all other terms. So in all other terms, if instead of x in this identity, we had a minus of 1 plus x, then this kind of a formation could have been conceived. Yes or no? You know what I'm saying? Right? Therefore, let's move in that direction, okay? That means in this, replace in this identity x by minus of 1 plus x. Are you averse to this now? Right? So if I replace x by minus 1 plus x, then I have 1 minus 1 plus x plus 1 plus x whole square on the left hand side. That's what we have on the left hand side, whole to power n, replacing x by minus of 1 plus x, as was the design, as was desired, right? And that must be a naught minus a1 into 1 plus x plus a2 into 1 plus x whole squared minus a3 into 1 plus x whole cubed a2n into 1 plus x to power 2n. Yes or no? So far so good? Now somewhere down the line I must be lucky enough, right? What is this? See, x square plus x plus 1 is what this is, isn't it? Right? This is x square plus x plus 1, which is the same as this. See, that's why I said somewhere down the line we need to have the nature favoring us, obliging us. Nature obliges. So 1 plus x square whole to power n, that's the left hand side. And the right hand side is a naught minus a1 into 1 plus x plus a2 into 1 plus x whole squared minus a3 into 1 plus x whole cubed plus a2n, sorry, this was a2n into 1 plus x to power 2n. The term prior to this would have been minus of a2n into 1 plus a2n minus 1 plus x to power 2n minus 1. Yes or no? Now this an also is what? The coefficient of x power n in this. So we equate coefficient of x power n in the identity. Coefficient of x power n on the left hand side is an, right? And coefficient of x power n on the right hand side, from this term I get a2n into 2n cn. From this term I get minus a2n minus 1, 2n minus 1 cn, and so on and so forth. We get this. So starting from the last term, moving backwards, equating coefficient of x power n on both sides, a2n into 2n cn minus a2n minus 1, 2n minus 1 cn, and so on and so forth. We're able to arrive at this. Got me? Does it make sense to all of you? Let's look at the next problem. Got me? Wipe this off. 1 plus x square to power 3n plus 1. Obviously, the highest power of x would be x to power 6n plus 2, as you can see. So this is a power series from x to power 0 to x to power 6n plus 2. Now what we want to establish is, given this, we want to establish summation twice a3r minus a3r plus 1 a3r plus 2 are equal to 0 to 2n equal to 0. Now realize that a3r plus 1, a3r plus 2, the thing that distinguishes a power 3r from a power 3r plus 1 and from a power 3r plus 2 is cube root of unity. That's the way. Do you realize? The way you can differentiate between a power 3r and a power 3r plus 1 and a power 3r plus 2 is with the help of omega, powers of omega, right? The way you group powers of omega to power 3k will give me one set of values, omega to power 3k plus 1 will give me omega to power 3k plus 2 will give me omega squared, and therefore the rule of the game is to be able to sieve 3r plus 1 and 3r plus 2, you must fall at the feet of cube roots of unity. You must seek help out of cube roots of unity. That's what you must do. Yes or no? That's the only way you can. I mean, if you have experienced a little bit of problem solving, you'll realize that 3k plus 1 and 3k plus 2 are distinguished out of omega. Omega sets them apart, right? And if you've been able to identify this, so remember this from now on. Every time you see the powers 3, see a3r here is the coefficient of x power 3r. a3r plus 1 is the coefficient of x power 3r plus 1 and so on and so forth. So how do you separate them? Cube roots of unity is the only way you can segregate these, right? Therefore, and one more thing, to get a 0 in an exam, it's easy, right? It's equally easy here. Again, you know how the pair of things will come and flash together. If you plug in x equal to omega here, it will produce a 0. And also if you plug in x equal to omega square, it will be 0. Yes or no?
Yes, sir.
Now, whether you plug in x equal to omega or x equal to omega squared, x power 3r in both cases will be 1. That means the a3r's will add when you put omega and omega squared. So that's why you will get 2a3r, right? So then a very nice feeling of euphoria, at least a temporary happiness. Put x equal to omega and x equal to omega squared in this identity and add. Put x equal to omega and x equal to omega squared and add. And there is rationale why we put x equal to omega and x equal to omega squared. It didn't come out of an angel. It came out of very basic common sense about being able to sieve 3r plus 1 and 3r plus 2. Omega is the tool that helps us differentiate, right? So plugging in x equal to omega and x equal to omega squared seems like a decent proposition in this identity. So if I plug in x equal to omega, for example, what am I going to get? 0. 1 plus omega squared is 0. So 0 equal to a0 plus a1 omega, a2 omega squared, a3 omega cubed, a3 therefore 1, right? a4 omega, a5 omega squared, a6, a3, a6c, and so on and so forth. Plug in x equal to omega squared. Once again, it will be 0 because omega and omega squared are both roots of this equation. So that will also be 0. That's a naught plus a1 omega squared plus a2 omega plus a3 plus a4 omega squared plus a5 omega a6. Shoot. Add vertically. When you add vertically, you love it. Because see, the 3k's, A0, A3, A6 get clubbed together. All the A3k's, there's twice A3k's, right? So, twice A0 plus A3 plus A6, etc. And now what about the rest? Right? Omega plus omega squared minus 1. So, A1, A4, etc. will belong to this. And then, what about this? A2, these are all 3k plus 2 form, A2, A5 and so on and so forth, yes or no? So then when you club them together, you will have like a minus A1 plus A4 plus A7, which are all 3k plus 1, etc. And then you will have like a A2 plus A5, which are all 3k plus 2, kind of a thing. So this is twice summation A3R minus summation A3R plus 1 plus summation A3R plus 2. R runs from 0 to n, etc. That's 0, which is what this is. Right? Copy. This is x equal to omega square. G was a problem that was posed in class 11 to us in St. Xavier's in one of our school exams. And this was not there in any book that we had. Our teacher might have sourced it from somewhere, God knows. But so, just a tribute to my teacher who posed this problem in the exam. Most of us actually could do this problem because by then they had taught enough calculus to us so that we could. In your case, calculus starts relatively late. That's because your class 10 has nothing that will enable early start of calculus. Okay, let's look at problem G. So obviously you'll start with 1 minus x power n, so the signs alternate. So that the signs alternate at least, right? Let's start with a 1 minus x power n. That's like a c0 minus c1x plus c2x squared minus c3x cubed minus 1 to power n cnx power n. Yes or no? Reason we started with 1 minus x power n so that the signs could alternate, right? Now, what we need is a 2 below this, a 3 below this, a 4 below this, etc. So then, okay, no, we don't need that. Sorry, we need 1 below this. So this x was no good. We needed only C1 here, right? We needed by 2. So if I integrated this, it will give me 3, but we need only a 2. So it would have been nice if this was x here. So what we do is, well, and then we don't need C0 on the right, on this side. So we club C0 with this, right? C0 is 1, we club with this. So what we do is 1 minus x power n is C1x minus C2x squared plus C3x cubed minus 1 to power n minus 1 Cnx power n minus 1 x power n. Sorry. And then of course, like I said, we need only a C1 here so that on integrating we get 1 in the denominator. We need only a x here so that on integrating we get 2 here. So we want to divide by x so that the powers are reduced by 1. Yes or no? Now of course, we want to be able to integrate both sides from 0 to 1, right? From 0 to 1 is what we want to do so that we have this, right, this left hand side available to us. So this side is fine, it takes care of the left hand side. Now the only task ahead of us is to be able to integrate this. 0 to a fx dx is f of a minus x. So replace x by 1 minus x in this, right? The property. Right, this is a GP series. Absolutely, 1 plus x squared plus x power n minus 1 dx. I hope you realize this is the sum of this GP series, and now when you integrate, it will be 1 plus half plus 1/3 plus 1 by n. Now I have another story around this where our teacher in St. Xavier's, he didn't give us full marks for doing this because in the exam paper he had written establish this without calculus. So he gave us some marks out of being a gentleman, but didn't award full marks to us. He said, no, I wanted, he had very clearly written without using calculus, show this. Now, although you know, in the current day context, it may not be relevant, but I'll tell you what you should do to show that the left hand side is equal to right hand side. I'll just get you started and don't spend time on it now. Call the left hand side un, right? Show that un minus 1 is 1 by n and add n equal to 1, 2, 3, etc. Call the left hand side un and then show un minus 1 is 1 by n. Put n equal to 1, 2, 3, etc. You will get 1 plus half plus 1/3 and so on and so forth. You will get a telescope. You know what I'm saying? Show this. Un minus 1 is 1 by n. Put n equal to 1, 2, 3, etc. and add vertically. You will get un is 1 plus half plus 1/3 and so on and so forth. That's what you will get. You don't have enough time right now, otherwise, you know, I would have asked you to work on it at home, but this is something that will work. Right? Have you attempted problems beyond this? No, not yet? So we'll stand by for a moment. H. Given 1 plus x square to power n is summation AR x power r are equal to 0 to n. We want to be able to find the value of minus 1 to power p AP NC 3r minus p. Now, AP is really the coefficient of x power p in this, isn't it? Huh? This will give me NC 3r minus p is the coefficient of x power 3r minus p in, let's say, 1 plus x power n. When I multiply these two, then I get like a coefficient of x power 3 somewhere, isn't it? Huh? Coefficient, something like that. Coefficient of x power 3r. Coefficient of x power 3r kind of a thing. So I need to bring x power 3r, and at the same time I want to bring C0, C1, C2 again with alternating signs. Huh? That's what I want to be able to do. See, 1 plus x square, if it's multiplied with 1 minus x, will give me 1 minus x cube. 1 minus x power n is C0 minus C1x plus C2x square and so on and so forth. I hope you realize where it's all sourced from. Now I multiply these two. I get 1 minus x cube whole to power n. That's equal to summation AR x bar r equal to 0 to 2n into C0 minus C1x plus C2x squared minus C3x cube and so on and so forth. Right? Now, if I have to look at coefficient of x bar 3r, if I have to look at coefficient of x bar 3r on the left hand side, what would that be? NCR minus 1 to power r would be the coefficient of x power 3r, yes or no, on the left hand side? Tell me. Because x cube whole to power r will give me x power 3r. Right? So coefficient of x power 3r on the left hand side is this. Right? Coefficient of x power 3r on the left hand side is this. And coefficient of x power 3r on the right hand side. See? If I have, let's say, AP, say just to AP P runs from 0 to 2n, say, right? So AP will give me x bar P, and then I need 3R minus P there, and 3R minus P will be obtained by C. 3R minus P, yes or no? You know what I'm saying? With every AP, you need C, 3R minus P, and minus 1 to power 3R minus P. That will give me x bar 3R. So coefficient of x bar 3R on the right hand side would be summation of NAP with NC 3R minus P into minus 1 to power 3R minus P. P runs from 0 to 2n, 0 to 3n, 0 to 3R, 0 to 3R. Equating coefficient of x bar 3R on both sides, yes or no? Clear now? See, minus 1 to power P, minus 1 to power minus P is the same as minus 1 to power P. This is minus 1 to power 3R, minus 1 to power R, that will give me minus 1 to power 2R, that will be just 1. So, this minus 1 to power P, AP, NC, 3R minus P would simply be NCR, will simply be NCR, right Kaushik? You know what I'm saying? I've equated coefficient of x bar R on x bar 3R on both sides, x bar 3R on both sides, that's all that we've done. Next, problem I, we are seeking to find n plus 2 C naught 2 to power n plus 1 minus n plus 1 C1 2 to power n plus n C2 2 to power n minus 1, etc. C naught minus C1 plus C2, etc. I'll tell you, I'll start with x minus 1 to power n in this case. So that x power n minus 1, etc. So I'll start with this here. We could have started with 1 minus x all to power n also. That would have been fine. So that's like C naught x power n minus C1 x power n minus 1 plus C2 x power n minus 2 and so on and so forth. Now with C naught, I need n plus 2. So yes, I multiply with x square and then differentiate, right? Multiply with x square, both sides. And then, as you would expect, differentiate both sides with respect to x. So when I differentiate both sides with respect to x, I get 2x into x minus 1 to power n plus nx squared, x minus 1 to power n minus 1, yes, n plus 2 c naught, x power n plus 1 c, minus n plus 1 c1, x power n, and so on and so forth. What would you next do? Put x equal to 2 on both sides. Put x equal to 2 on both sides. If you plug in x equal to 2 on both sides, you get the right hand side as desired. Right? Put x equal to 2 on both sides. So, but you know, binomial theorem is a little bit of a scientific art. You know, with the cleverness of science and the imagination of art, you will have to flush the two together. You know, that's why binomial theorem requires a little more maturity than other topics. So far so good, right? Can I write this off? NC R minus 1, right? Run to n, and we want to be able to find F30. Simple observation. See this NCR with this NCR, R squared plus 2R plus 1 is R plus 1 whole square, right? Can I write this as summation VR minus VR minus 1, or you can say VR plus 1 minus VR if you like, R equal to 1 to n. Can I say this? Telescope, where VR plus 1 is R plus 1 whole square into NCR, that's VR plus 1. Therefore, VR would be obtained by replacing R by R minus 1, which would be this term. So, we will have R equal V2 minus V1 plus V3 minus V2, so on and so forth. And you can add telescopic cancellation of terms and you will get Fn exclusively as a function of n, and then put n equal to 30. Simple? Right now? Yes. Because this I can write as NCN, n plus 1 Cn, which is just the coefficient of x power n in 1 plus x power n plus 1 plus x power n plus 1. Yes, 1 plus x power n plus k. How many terms? K plus 1 terms in this summation, right? K plus 1 term. So which is like coefficient of x power n in minus x, right? Clear? Which is, so instead of seeking x power n in this, coefficient of x power n plus 1 in the numerator. So we essentially would want to have coefficient of x power n plus 1 in 1 plus x power n into 1 plus x power k plus 1 minus 1. Absorb the minus sign here, right? So this will not give n plus 1. This is 1 plus x power n plus k plus 1 minus 1 plus x power n. So coefficient of x power n plus 1 will not appear here, will only appear here, right? And coefficient of x power n plus 1 here is going to be n plus k plus 1, see, n plus 1, which would be the required summation. Got me? Right? Fairly easy. Let's look at the next problem. Can I wrap this off? Root C1 plus root C2 root Cn less than or equal to n into 2 to the power n minus 1 whole to the power half. True or false? Huh? See one thing. In an exam, if nothing occurs to you, check with two terms and some simple values, right? Although, that goes against my value system. But in the current day context, a pragmatic approach to life and to things in general would be to find easier, though inferior shortcuts to things, right? So in an exam, you could do that. But in the class, let's do mathematics. Okay? Essentially, what are you trying to show? Whether this is less than this or not? This is like 1 into this plus 1 into this plus 1 into this. Right? That's what. Now, this is summation AI BI whole squared. Yes or no? Where the AIs are 1, 1, 1. The BIs are root C1, root C2, root Cn. Right. Cauchy-Schwarz inequality. Summation AI BI whole squared. Summation AI BI whole squared less than or equal to summation AI squared into summation BI squared. Right? So this is summation AI BI whole squared, which is less than or equal to 1 plus 1 plus 1, which is n. And then into C1 plus C2 plus Cn, which very clearly is 2 to the power n minus 1. So this is so true. Alright? So Cauchy-Schwarz, don't forget. The friend always. Summation AI BI whole squared less than or equal to summation AI squared into summation BI squared. Actually, there was a similar problem in the last sheet, and that problem, our friend Abhirup, in his absence, let me just say, he was trying to do using Cauchy-Schwarz, so he got here. So that's when I thought, okay, now this class, I'm going to include Cauchy-Schwarz. The same thing, I'm going to convert it to Cauchy-Schwarz and give it to you. So I thought, he'll be mentally distracted from what he did in the last class, because Cauchy-Schwarz didn't work for him in the last class, so I thought, he will continue to believe that it will not work. So this time let me put Cauchy-Schwarz and see if he takes it in the right spirit or not. He's not there though. So this was essentially for him to now re-ensconce and re-establish his faith in Cauchy-Schwarz. Twice 1 plus x cubed to the power 100 is summation I equal to 0 to 100 ai xi minus cos of this. We want to find the value of A0 plus A2 plus A4 plus A100. That's what we want to be able to do. There are times that they add things only to make them look ostentatious, gaudy, and difficult to approach. But this problem is actually very simple. I'll tell you what. In this, replace x by minus x. On replacing x by minus x, then add. Cosines will walk out of your life for the time being. If you add, then please watch that. See if the cosines get cancelled or not. And then put x equal to 1. And then put x equal to 1. The even powers, the even coefficients will automatically serve you. Add this, put x equal to 1, and enjoy life from this point onwards. Right? Much for today. Oh, I want to have a session on gravitation problem solving.